All right, good afternoon, everybody. By the way, okay, so this class is at 3 o'clock, and you know that because you're here right now. I was looking at the schedule that all of you have. There's a way for me to kind of aggregate everybody's course schedule all at once. And I noticed, at least last time I checked, nobody has a class at 1. Is that right? That's not right. Okay, nobody has a class at 1, so that's right.
So we're going to move it? Can we move it?
Well, I'm curious to know whether you'd prefer to have our class at 3, like we're doing now, or at 1.
You're messing with my caption.
All right, so I'm going to send around, not now, but next week, we're gonna have a secret ballot because somebody may not want to speak up that actually. Some of you really want 1, but we can only make the change if it's unanimous. Like if it wouldn't inconvenience everybody. So I just wanted to get like an initial feel for that to see if it's even worth looking at it a little bit further. So on Wednesday, we'll revisit the topic.
Okay.
Speaking of Wednesday, your homework assignment 1 is due on Wednesday, and we're not going to be meeting on Monday. Monday is a holiday, so we won't have a lecture that day. But as you're working on homework 1, if you have questions, you can feel free to email me. I will be in my office on Tuesday, so you can stop by if you want to see me on Tuesday. Even though I don't have office hours, I'd be glad to see you that day. Today we're going to be talking about flow resistance and the relationship between velocity distributions and how the water interacts with the pipe depending on the thickness of the boundary layer. So you may have seen already that in the homework assignment there's a couple of things having to do with the thickness of the boundary layer, and we're going to go over some methods related to that today. So before we get into it, are there any questions related to the announcements or anything else? All right. The Chezy equation is an empirical approach that's used to characterize the effect of pipe friction. So the Darcy-Weisbach equation is the most accurate, that friction factor F that you can find with the Moody diagram. That's the most accurate empirical method we have for estimating how pressure may be changing due to pipe friction, but it's certainly not the simplest. And back in the early days of engineering, when they were trying to come up with equations that would describe what effect pipe friction is having, one of the first approaches was the Chezy equation. And I mention it because occasionally you may find some references that still use a Chezy roughness coefficient to describe how rough a pipe is. And so the units on the Chezy roughness coefficient is length to the 1/2 power divided by time. And so when you use the Chezy equation, what you're going to get is the velocity of flow through a pipe where the hydraulic radius of the pipe is one of the parameters, the roughness coefficient, and then S sub F. Remember, there's 3 different slopes we'll be talking about this semester. There's the pipe slope, the water slope, and the slope of the energy grade line. Which is S sub F? It's the energy grade line. So in closed conduit flow, even when you have steady uniform flow, the slope of the energy grade line can be independent of the pipe slope. So the pipe may be horizontal, but the energy grade line is going down as the pressure is decreasing in the direction of flow. So the slope that this is talking about is the slope of the energy grade line, and that's kind of the gradient that causes flow. That's the driving force that would give us a velocity. Okay, now the C value, a high number is a low roughness, and the way that you know that is that a high C value would give you a larger flow velocity through a certain pipe. And so if the slope of the energy grade line is how steep the energy loss graph is, and if you have a really steep energy loss gradient, then you're going to have higher velocities, and the roughness also plays a role in the velocity. So a low C value gives you lower velocity, high C value gives you faster velocity. One of the disadvantages of the Chezy equation is that C values are different depending on which unit system you're using. And that's not the case when it comes to F values or even later on when we talk about the Manning's equation, Manning's n values are also independent of the unit system. So that's one of the reasons why the Chezy equation isn't really used so much anymore, is just the inconvenience of having separate roughness tables for both the SI units and the English units. But it was this Chezy idea that Manning later built on, the idea that the velocity of flow is going to depend partly on the slope of the energy grade line, partly on the hydraulic section, meaning like the geometric parameters of cross-sectional area, hydraulic radius, and then this ambiguous roughness factor, where we know certain surfaces are going to drag the water more than a smooth surface will, exert a larger shear stress on the water. There is a equation in your textbook that relates the Chezy equation with the Darcy-Weisbach friction factor F. So if you ever need to convert between the two, it is possible. They set the head loss due to pipe friction equal to each other and solved for C, so that's where that relationship comes from. But just so you know, it is available in the book. Well, let's talk a little bit more in depth about flow through a pipe and velocity distribution. You probably remember back in fluid mechanics the idea of the no-slip condition. And that is, if you have a fluid that has viscosity, you can't have it changing velocity suddenly. The velocity changes across a cross-section have to be gradual. And this profile is showing that at the edge of a pipe, so down here at the bottom edge of a pipe, the velocity is 0. The water velocity has the same velocity as the pipe, which the pipe is stationary. And so the further away you get from the edge of the pipe and the closer you are to the center, where there's less influence of those pipe walls dragging back the fluid and exerting pipe friction, the further away you get from the edge of the pipe, when you're in the center of the pipe, the velocity is faster. And so there's a variety of different shapes. If you have turbulent conditions, then the velocity profile may be more logarithmic compared to laminar conditions, where if you have slow-moving flow, then the distribution is parabolic. But the important thing is that when I've given you this formula before for Reynolds number, RE, I guess it's on the screen there, velocity times diameter divided by kinematic viscosity, which velocity did we use in that formula? For instance, during the fluid mechanics lab, where you had that vertically inclined clear pipe and we were injecting the dye downward, what velocity did you put into the equation when you were solving for Reynolds number? Do you remember how you found that velocity? What's that? It's the mean velocity. Right. So the way that we got that velocity, we didn't measure it directly. What you did is some volume accumulated in some amount of time. And so from that measurement, you got flow rate. Right? You remember the dropping the... Actually, I think we used the funnel and the graduated cylinder because the flow rates were so small. So a certain volume in a certain amount of time gave you the flow rate Q. And then we knew the cross-sectional area of that little tube. Right? We knew that the area is pi d squared divided by 4. And so you got that mean velocity by having Q divided by the area. So that was the mean velocity. These profiles show us that there isn't one velocity inside of a pipe. There's lots of different velocities. And so the velocity at the center of the pipe is going to be completely different from the velocity at the edge of the pipe. And so the Reynolds number doesn't just have to be applied across the average of the entire section, but there's going to be a different Reynolds number at every point in the pipe. So here at the center of the pipe, the Reynolds number is high, and you may have really turbulent conditions at the center of the pipe. Why would the conditions be turbulent at the center? It's not because the kinematic viscosity is any different, and it's not because the pipe diameter is any different. What changes at the center of the pipe that makes it more turbulent at the center of the pipe than at the edges?
There's no obstruction.
It's more velocity, and the velocity is going faster because there's no influence due to pipe friction, or less. But the closer we get to the edge of the pipe, the velocity is lower, and so the Reynolds number is lower. So last semester when we did that experiment, we had a certain flow rate and we said conditions are laminar or conditions are turbulent. And that was a simplification because on average maybe they're turbulent at a certain flow rate, but there's a point inside that pipe. There are locations where it's still laminar flow. Even if on average, like if most of the spots in the pipe are experiencing a high enough velocity that conditions are turbulent, in most of the spots, there's still a few places where the conditions are laminar. So where's that going to be? Where is it in the pipe that even when the whole rest of the section is turbulent, it's laminar in some just rare spot? Where is that special spot that the conditions are still laminar?
Along the edge?
It's in the edge. Exactly right. Very good. So here is a graph of that. Now this is a difficult figure to understand immediately, but I think that we'll get there. On the horizontal axis is shear stress. Remember, shear stress is the resistance. The pipe is pushing back against the movement of the water. So if the water is flowing to the right, the pipe is pushing on the water to the left. It's resisting flow. The closer we are to the edge of the pipe, the more resistance there is. So the shear stress is at the highest right at the edge of the pipe. So down here at this bottom boundary, there's a lot of shear stress, but then the further away we get from the edge of the pipe, now this is showing at the center of the pipe, there's the least shear stress. So far, is that consistent with what we know about velocity profiles? It is, because the velocity says there's the highest velocity at the center of the pipe. I mean, it goes hand in hand. There's the highest velocity at the center of the pipe because there's the lowest shear stress. And remember, a shear stress exerted over an area is a shear force. So what is causing resistance is force, and that force was imparted by a stress exerted over an area. All right, so this curve, or this profile, is just what the shear stress profile looks like for a certain flow rate. If you're putting 10 liters per second through the pipe, then we could come up with a graph that shows, as a function of distance from the edge of the pipe, what is the shear stress. So how much resistance is there for a certain flow? And so this is saying, this is what the shear stress profile looks like if you have turbulent flow through the pipe. Even if most of the pipe is turbulent, there's still going to be laminar flow in the vicinity of the edge of the pipe. And that's the most important thing from today's lecture, is that there's still going to be this layer. You see that, anybody really good with Greek and know what symbol that is?
Delta.
Is it? Delta? I forgot.
I think it's baby delta.
Baby delta. Let's call it that. Okay, so the thickness of the boundary layer changes depending on the velocity through the pipe. So if you have really fast moving flow, it may just be a tiny little section that has laminar conditions, like really close to the edge of the pipe. But if you have pretty slow moving flow, maybe only the center of the pipe is turbulent, and then there's this thick cushion of a laminar layer. So you can think of this delta, the thickness of the boundary layer, as getting bigger or smaller depending on the bulk average velocity inside of the pipe. And the boundary layer is sometimes called a laminar sublayer. So it's the region where we have a Reynolds number less than 2,000. And the thing that's significant about that is that sometimes the roughness elements for the pipe are going to be fully submerged inside of that boundary layer, and sometimes they're going to protrude out of the boundary layer. So if we have fast flow velocity through the pipe, then the boundary layer will be small, and if the velocity through the pipe is moving slowly, that would give us a thicker boundary layer. Any questions so far about the general concepts? Okay. Now, different materials have different roughnesses, and we've talked about the K sub S to D ratio, which is that left vertical axis on the Moody diagram. Here, K sub S and epsilon are used interchangeably depending on the text that you've got. These are different materials and their typical equivalent sand roughnesses. And we talked about equivalent sand roughness in fluid mechanics. In fact, when we were looking at water gems for the first time, I showed you how there's a library of materials, and it had that equivalent sand roughness for a whole lot of different materials. So what it means physically is that if you were trying to represent how rough, for instance, a galvanized iron pipe is, what you could do is you could have these spherical sand grains that have a diameter of 0.15 millimeters. And if you somehow were able to glue those circular spherical sand grains to the edge of a perfectly smooth pipe, it would take a diameter of 0.15 millimeters of sand to be an equivalent roughness to, on average, how rough galvanized iron is. So certain materials like glass or copper, brass, they're known for being very smooth and not exerting as much pipe friction effect as materials like wood or a rough concrete, where the equivalent sand roughness is much larger. And it's hard to believe that, yes, in fact, they used to make pipes out of wood. I'm sure everybody knows like barrels can be made out of wood for like aging whiskey or aging wine, but there was a time where it was pretty common for water delivery to also be made out of wooden pipes, and they'd coil metal around the outsides to try and keep all of the planks together. Of course, you couldn't pressurize a pipe very well. It was essentially gravity flow, or at the very least just a low head. But it would be interesting to know if there are still any sections of pipe that have wooden for delivering drinking water. I'd be shocked if any place in the United States has wood for drinking water. There still may be a handful of places that have it for wastewater, where the stakes are a little bit lower. In any case, what we're going to look at is ways to estimate how thick the boundary layer is. Morris and Wiggert have an approach for calculating the thickness of the boundary layer by estimating the shear velocity. And remember, we talked about the shear velocity last time. It's where we're describing the shear stress with units of time, length per time. So they express it as a velocity by having the shear stress divided by the fluid density. So if you can know the shear velocity of the fluid and the fluid's kinematic viscosity, then they say you can estimate the boundary layer thickness with 11.6 times the kinematic viscosity divided by shear velocity. This isn't a fundamental equation. This is just based on observation. And so this is an empirical equation, which is a guess. They came up with this equation by just fitting observations to the best fit function that they could come up with. So that thickness of the laminar layer sometimes fully submerges these roughness elements. And so in this previous slide, we said, this is how rough different materials are. So you see these little ridges. You can think of that is the roughness elements on maybe, for instance, a concrete pipe. It is possible that if you have slow-moving fluid, then your laminar zone is thick and it fully submerges the roughness elements. And that's what we would call hydraulically smooth. If we know that the laminar layer is more than 1.7 times the thickness of the material, then it's definitely hydraulically smooth. And by contrast, if it's less than 0.08 times the roughness, then that's hydraulically rough. So there's a pretty big no man's land in the middle there. And in some ways there's an analogy there to laminar, turbulent, and then the transition region. You remember how there was a transition region between 2000 and 4000 where it's not necessarily laminar and it's not necessarily turbulent? This is the same thing. What we're doing is we're describing three different conditions. We're describing the hydraulically smooth condition, there's the hydraulically rough condition, and then an indeterminate range in between. But the reason why we distinguish between these is that the head loss performance is very different if, you'll notice in the hydraulically rough, the roughness elements are sticking well out of the thickness of the boundary layer. The boundary layer is only 8% of the thickness of the roughness elements, whereas in the case of hydraulically smooth, it's almost double. The boundary layer is almost twice as thick as those roughness elements. So once we are able to calculate the thickness of the boundary layer, then later on in the semester, we're going to look at what are the consequences of that, because there are certain assumptions that we can make, like when calculations are really complicated and we're trying to find the friction factor F. Sometimes we don't know what friction factor to use because we don't yet know the velocity through the pipe. If you don't know what velocity the water is going through the pipe, then you don't know the Reynolds number. And remember from the Moody's diagram, if you don't know the Reynolds number, you can't find F. So it's like a classic chicken and the egg scenario where you don't know F because you don't know the velocity, and you don't know the velocity until you know F. And so, like we're stuck. We have two unknowns. And so whether conditions are hydraulically smooth or hydraulically rough sometimes gives us a clue on how we can break that cycle and start calculations with a reasonable assumption. So that's why we bring it up, is because eventually we will make an assumption about the flow being hydraulically rough, and then that allows us to continue when we have a lot of unknowns and we can iterate a solution. Any questions about the concepts of a boundary layer? All right. So the example that we're going to work today, this one we have an elevated storage tank, a building on a hill. So this should look pretty familiar if you've already glanced over the homework assignment. I think your homework problem is an elevated tank connected by pipe to a building on a hill. What we're given here is the flow rate, and we know that we need a pressure of 350 kilopascals, and it says that that pressure is needed at the ground floor. Okay, so we've got that the elevation of the ground floor is 20 meters above some datum. The pipe is 250 meters long, the diameter is known, and the friction loss is 16.4 meters. All right, so if you just know H sub F and you're not yet having to calculate it, then what would be the water surface elevation that's required here inside of the tank? That's what we're asking in part A. Next, in part B, if you're knowing that the friction loss is 16.4, then find what would be the F value that corresponds to that given loss. So you're kind of just back calculating for F in part B. And in part C, I want us to get some practice by in calculating the thickness of the boundary layer. So what you'll have to do, first of all, is calculate the shear stress. And then you'll have to calculate the shear velocity. And once the shear velocity is known, calculate the thickness of the boundary layer. So that's our practice that we're going to get in part C. All right, so I'm going to pause the recording. The time is yours to collaborate and to run the numbers here. We're going to just try and find out how tall does the tank have to be to force the water through that pipeline and make sure that we have an adequate amount of pressure at the base of the building. In the tank, you've got the picture. So just think it's like a big tank, and the water isn't going down, or if it is, it's only going down really slow.
the velocity here, the water is moving, it's still in the pipe and it's moving, so that's why that's why I don't cancel out V2, but I do cancel out V1.
See, in my mind, I just equals each other, so they would be non-equals at the opposite sides.
Wait, how come the math came out the same or similar?
Well, it's because the velocity head at 2 is only 0.8 meters, so it's pretty small.
That's why we were at 72, we got 72.9. We were missing that section, 0.8.
Yeah, so there's no velocity head in a big pool of water like that. But the water still does, it's moving through the pipe, and so I said the velocity head at 2. That's right. If it was stopping, there wouldn't be head loss.
Okay.
We were close, but
Yeah.
I just think
So this is in the micro.
Okay, so for part B, what is the friction factor? We can rearrange with the known head loss and the known flow velocity, the known pipe length, known pipe diameter. It says that the F value should be 0.0194. And so that's how they would calibrate, is they can measure all of these things. They can measure, for instance, what's the pressure in the pipe downstream, and then you could kind of extract an understanding of the F value based on that. The third part was asking what is going to be the thickness of the boundary layer. Let me zoom in here so it's a bit easier to see.
we see that boundary layer.
All right, so S sub F, the slope of the energy grade line, is going to be the head loss of 16.4 meters divided by the pipe length of 250. So we got a slope of the energy grade line that's going to go into our calculations of shear stress. So the unit weight of water, typical 9810. We don't have any distinct information about like an unusual pipe water temperature or anything. Hydraulic radius here of 0.0625. That can just be the diameter divided by 4, since it's a circular pipe that's flowing full. We don't have to go to the trouble of calculating the cross-sectional area and dividing by the wetted perimeter. It's for a circular pipe that's flowing full, it's just D divided by 4. Substitute in the slope of the energy grade line, and here's the shear stress that's occurring. Convert that to a shear velocity by dividing the shear stress by the density of the fluid and taking the square root. So Morris and Wiggert's estimation is that the thickness of the boundary layer is going to be 5.8 times 10 to the minus 5th meters, and so that's really small. The thickness of the layer that's laminar is going to be 0.058 millimeters. And now let's just compare that to some of the typical thicknesses. These are in millimeters as well, so 0.058, I guess that is, if it was a glass tube or copper or brass, we might still have those elements fully submerged by the laminar layer, but all of the rest of these, the laminar layer is going to be projecting and protruding, excuse me, the elements. You can think about it like mountains. Are the mountains sticking out of the fog? Like the fog is the thickness of the laminar layer? The mountains are sticking out of the fog for all of these, with the exception of, I guess, the wrought iron and the glass, because it was 0.058 millimeters. Okay. Any questions on the example? Yes?
Where did you get 1 times 10 to the negative 6?
That is a constant. That's the kinematic viscosity of water, and it varies as a function of temperature, but it's something you can look up in the back of your fluid mechanics textbook, like the dynamic viscosity of water is 1 times 10 to the minus 3rd Newton seconds per meter squared, and the kinematic viscosity is dynamic divided by density. So in other words, it's just a constant. Yeah. Question over here? Same thing. Where'd this come from? Yep. Good. You've got Monday off. Wednesday the assignment is due, so just let me know if you have any questions. I'll take my laptop home over the weekend and I'll just be waiting. Just be waiting for your emails.
Just sitting there like...
Just sitting there. Don't leave me hanging. All right. Have a good vacation. I'll see you on Wednesday.